Hi, I'm Blake Thompson with the Oklahoma State Air Raid, the senior design team for the 2020 Argonia Cup. Our team is comprised of 7 members, split into 3 sub-teams. We have the rocketry sub-team, the aerodynamics sub-team, and the CAD manufacturing team. This team was assembled on January 13th, beginning of the spring 2020 semester. We're in the middle of manufacturing right now and currently on track to compete at the end of March. A brief overview of our system. We'll have a rocket. It will take off, climb to apogee, and our recovery system will deploy. The rocket will come down under its own parachute and land wherever it may, and the recovery system will make its way to the predetermined location.
Hi, I'm Kyle Moose. I'm part of the aerodynamics team. For our payload delivery system, we had multiple ideas. Our first one being a quadcopter. The 2018 OSU team also had this design and actually pursued it. We've decided that we don't want to do it though because we see a lot of the issues that they had with deployments and with the electronics configuring and orientating themselves up at the 8,000 feet in the air. And so we decided to go with another idea. One of the other things we looked at was a paraglider. We like the paraglider design because it's very controllable and has a tight turn radius, but we think that there could be a lot of issues up at our apogee point when it deploys if there's strong winds, because strong winds will carry it too far away, and then it has a poor glide ratio, so it won't ever come back to the target and get close to that. Given that we didn't like those 2 designs, we decided to go to a glider configuration. We like the glider because it has a good glide ratio, it's light, it's easy, and it's maneuverable. So for our glider, there's multiple different options that we can do. We can do a standard glider, a canard, or something based on the Raytheon Coyote. We really like the Raytheon Coyote because it gives us 2 different surfaces to lift and control off of, and we believe that the swing out design is perfect for deploying out of the rocket.
Hi, my name is Jarrett. I'm on the rocket sub-team. Here's our rocket. We're going to be using the same rocket that they used in the 2019 Cup last year. Our dimensions, our height is going to be 87 inches. Our diameter is going to be 4 inches. The motor we're going to be using is a Cicerone L1050 or equivalent. Kind of depends on what we decide on right before the Cup. Here is a depiction of our rocket. As you can see, the red circles are where separation will occur, and the green circle is where our rocket's going to stay together. And at apogee, for our glider, we're going to be using a black powder charge. As you can see here, this red circle, this nose cone is attached to our glider. And like I said, at apogee, it's going to eject and come out.
Hi, I'm Steele. I'm also part of the rocket sub-team here. Here is a depiction of our rocket. We modeled it using Open Rocket. It is an apogee of about 9,500 feet with a max velocity of about 0.98 Mach. Our stability is 1 with a center of gravity about 60 inches after the nose and a center of pressure about 64 inches after the nose. So using Open Rocket, and we estimated the average wind values in March in Argonia, Kansas is about 15 miles per hour. We were able to get a performance estimate of an apogee of about 9,500 feet at about 20 seconds of flight time. And for our motor, we have a burnout time of around 4 seconds.
Hi, I'm Griffith with the aerodynamics team, and this is our glider. So as you can see, it's about 38 inches long with a folding wing design. The airfoils themselves are an NACA 4415 with a span of 32 inches and a chord of about 3 inches. So the ailerons will be roughly 5 square inches in size with a rear wing with a symmetric airfoil and a span of 12 inches that you'll see in a later design. Chord, 3 inches on that as well, and overall you'll see that the max takeoff weight is roughly 4 pounds with an aerodynamic center about 14.25 inches from the nose cone tip with a CG roughly around that area as well, creating a neutral point somewhere in the middle right here, about 18.75 inches. Leading into glider preliminary stability, we have a performance estimate of a bank turn around 40 miles per hour. This will give us a turn radius of around 150 feet with a roll angle of 35 degrees. So for our stability characteristics, as you can see in this curve, it'll show that we are statically stable in pitch at around 5 degrees angle of attack. That leads us into how we will actually control this flight. We will be using an off-the-shelf Pixhawk 2 Orange Cube autopilot system on a mini carrier board attached to a ground station with ArduPilot Mission Planner. We chose ArduPilot for its versatility and simple user interface that allow us to actually change the mission during our profile to achieve our best area for the attack angle into the landing zone. We chose the Orange Cube for its triple redundant sensors. In the past, we've had issues with GPS lock or any other sort of lock. So adding in redundancy allows us to really ascertain the best glide characteristics.
Hey y'all, David here, head of the CAD team for our glider. As the glider must be able to fit inside the rocket body, the most important constraint was size. Starting from the base constraint of a total length of 38 inches and a maximum diameter of 4 inches, the glider was modeled with constant communication with the aerodynamics team in order to ensure that the critical placement and dimensions of flight components were made. As it must fit inside the rocket body while folded, the best solution was a spring mechanism for both the main and tail assemblies. Assembly of the wing had to include the control surfaces along with the service to move them, while retaining the required strength along the length. This was done by adding a carbon fiber spar to both the main and tail airfoils. The electronics housing was designed to give maximum strength as well as ease of access to components with the nose cone removed, and the integration of key components such as the antenna for telemetry and communication to the ground.
Thanks for watching.
We'll see you in Argonia. Oh, hey, didn't see you there.